Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclair.
Welcome back to Teolumen Insights. Today we're going really deep into the work of Dr. Jonathan Phillips.
Yeah, really fascinating stuff. I'm excited to dig in.
He's a research professor who's really shaking things up in the physics world. We're talking about his exploration of atoms,
electrons,
and even the possibility of a revolutionary new energy source.
Which is a really big deal, right?
Yeah.
So we'll be unpacking some pretty mind-blowing concepts from Phillips' work with Randall Mills's Grand Unified Theory of Classical Physics.
Or GUTCP for short.
Exactly. Get ready to kind of rethink what you know about atoms, electrons, and even the possibility of this new form of energy.
Called Hydrinos.
Hydrinos, yeah.
Which is, honestly, it sounds like something straight out of science fiction, right?
It kind of does. But before we can get to Hydrinos, we need to lay some groundwork. Today, we'll focus on how Phillips uses GUTCP to explain the known world.
The world we're all familiar with.
Right, of atoms and ions, and how that differs from what standard quantum mechanics tells us.
So essentially, we're going to see a clash of the titans here.
Sure.
GUTCP versus SQM, or standard quantum mechanics.
Exactly, it's a head-to-head.
Yeah, and GUTCP really throws out the rule book of standard quantum mechanics. It claims that everything, literally everything, from tiny atoms to the vast cosmos,
can be explained by classical physics?
Classical physics, yeah. The physics that was developed before 1872.
It's a pretty bold statement.
It's a huge statement, right? And what I find really fascinating is that Phillips actually insists on only using equations.
Yeah, he really sticks to his guns there.
That were developed before 1872.
No fancy quantum math allowed. He's really serious about that.
Yeah, so we're talking no Schrödinger equation.
No quantum mechanics allowed.
No wave function.
No, none of that.
No uncertainty principle. So going back in time to a simpler, more deterministic view of the universe.
Right. I mean, how does it hold up to the experimental evidence? That's the big question.
That's what I'm wondering, too.
Right.
That's what Phillips sets out to test in his work.
He really does.
And he meticulously compares GUTCP predictions to established data. For example, ionization energies, which is the energy needed to remove an electron from an atom.
It's a pretty fundamental concept in atomic physics.
It is, yeah.
Yeah.
So it's not just theoretical. He's putting this to the test in the real world. So what did he find? What does Phillips find?
Well, he finds something pretty remarkable. I mean, using just two basic equations, like one for force balance and one for the conservation of angular momentum.
Two equations?
Just two, yeah.
Wow.
Phillips accurately predicts the ionization energies for all sorts of single electron systems.
So for hydrogen, it works.
It works.
But hydrogen's the simplest atom, right?
It is, yeah, that's the starting point.
What about more complex atoms? What about multiple electrons? Surely classical physics, those two equations, can't handle that kind of complexity, right?
It's the challenge, right? And this is where GUTCP really starts to really diverge from standard quantum mechanics.
Okay, I'm listening.
You see, SQM, standard quantum mechanics, has to rely on these really complex calculations.
Oh, boy.
I know, right? And what are called adjustable parameters to make their models fit the data?
Adjustable parameters, so they're kind of like tweaking the model.
It's like you're fitting a curve, but you have all these knobs and dials that you can adjust to get it just right. You know what I mean?
Yeah, match the data.
Yeah, to match the data points perfectly. But that makes me wonder, if you're always adjusting your model
After the fact.
right after you've seen the data.
How can you make accurate predictions?
Exactly. That's exactly the point Phillips makes.
It makes you wonder if you can really trust those predictions, right?
Right. And here's the big difference, right? GUTCP. It relies on purely classical principles, like those two equations. No adjustable parameters needed.
Interesting.
So it's a first principles theory, meaning it's based on those fundamental laws of physics, not on tweaking the model to fit what we observe.
Okay, so no curve fitting, no fudging the numbers. That's a bold claim, to say the least. How does it hold up for those more complex atoms, the ones with more electrons?
Well, this is where it gets really interesting, because Phillips tackles helium next, which has 2 electrons.
Okay, so 2 electrons instead of 1.
Exactly. And once again, the GUTCP model, with its unique understanding of how electrons interact, accurately predicts those ionization energies.
Helium with 2 electrons is already a big step up in complexity from hydrogen, right?
Yeah.
If GUTCP can get that right, doesn't that raise some serious questions about the standard model?
Absolutely. I mean, SQM, standard quantum mechanics, it really struggles to explain even simple atoms like helium without using those adjustable parameters. So the fact that GUTCP can do it, it's a big challenge to that prevailing paradigm.
Okay, so I'm starting to see why this GUTCP is such a big deal. So let's talk about the electron itself. How does GUTCP reimagine this fundamental particle?
Okay, so the GUTCP electron is not that fuzzy probabilistic cloud that we're used to from standard quantum mechanics.
Right.
It's something completely different.
Okay.
It's actually this tiny spherical bubble of charge.
A bubble.
Yeah. It's called an orbit sphere.
An orbit sphere. Okay.
And it's a really different picture, right? Instead of this fuzzy cloud, imagine a soap bubble. But instead of soapy film, it's pure electric charge with current zipping around its surface.
So those currents are what give the electron its spin and its magnetic moment.
Exactly. So in GUTCP, electrons have a very definite shape and a location. So there's no more of that quantum weirdness.
That's a much more intuitive concept.
It is, yeah. But remember, this is still just a theory, and it needs to be tested rigorously.
Right, of course. More research is needed.
But the fact that it can explain these things, like ionization energies, without resorting to adjustable parameters, that's pretty intriguing.
So hydrogen and helium, check. Where does Phillips go from there?
He doesn't stop there. I mean, he goes on to tackle lithium, which has 3 electrons and even larger atoms. And he consistently achieves this remarkable accuracy in predicting ionization energies using GUTCP.
All of this without using any adjustable parameters.
Yeah, that's the really incredible part. I mean, if Phillips is right, it's a testament to the power of classical physics.
It really makes you think differently about how we understand the universe, doesn't it?
It does. And speaking of thinking differently, one thing that really struck me was Phillips's discussion of the correspondence principle in standard physics.
Right, the correspondence principle.
He says GUTCP just throws it out the window.
Okay, I'm not sure I follow. What's the correspondence principle?
So basically it says that quantum mechanics should smoothly transition into classical physics as we go to larger and larger systems.
Okay, so as things get better.
Right. In other words, those quantum effects should become negligible at those macroscopic scales, like the world we see around us.
So it's like there are 2 separate sets of rules, one for the microscopic world and another for the macroscopic world.
That's one way to look at it. But Phillips argues that GUTCP doesn't need a correspondence principle.
It doesn't.
No, because it uses the same set of rules that classical physics to explain everything, regardless of scale. It's truly a unified theory.
So no need for this kind of arbitrary distinction between the quantum and classical realms.
Exactly. Everything is governed by the same fundamental laws.
And that has some pretty radical implications, doesn't it?
It really does. I mean, it means that things like quantum entanglement, which seem to completely defy classical physics,
They do.
could potentially be explained using those classical concepts.
If that's true, that would really shake things up in the physics community.
For sure.
But okay, let's get back to the atom. We've talked about electrons and ionization energies, but what about the nucleus?
Okay, so the nucleus. That's another area where GUTCP really diverges from standard quantum mechanics.
I'm sensing a theme here.
Yeah. In SQM, the nucleus is held together by the strong nuclear force, which is one of those fundamental forces of nature, right?
Right.
But GUTCP has a different explanation.
What is it?
Well, Phillips argues that the strong nuclear force isn't actually a fundamental force at all.
It's not.
No, he thinks it's something else entirely. He thinks it emerges.
Emerges?
Yeah, emerges from the electromagnetic force.
Wait, so one of the fundamental forces of nature is actually a manifestation of another force?
Yeah, that's a pretty big claim.
It is, yeah. That's a huge claim. What are the implications of that?
Well, it means that potentially the nucleus could be manipulated using electromagnetic fields.
That's not possible, according to standard quantum mechanics.
Not really, no. This is a pretty radical departure.
It really is.
Yeah.
If this is true, the possibilities are huge, right? I mean, for energy production,
Yeah. Material science.
even medicine. Everything could be revolutionized.
Absolutely.
It's pretty exciting to think about.
And it's just one example of the potentially revolutionary implications of GUTCP.
So we've got atoms, we've got electrons, and the nucleus all reimagined. But there's one more piece of this puzzle that we haven't talked about yet. The hydrino.
Ah, yes, the hydrino. That's where things get really interesting. And that's actually where we'll pick up next time.
Perfect. Can't wait. So join us for part 2 of our deep dive.
Where we'll delve into the world of the hydrino.
and explore even more mind-bending implications of this revolutionary theory.
I can't wait.
I can't either. This is going to be good.
It is. Welcome back to Teolumen Insights. We're continuing our exploration of Jonathan Phillips's work with Randall Mills's grand unified theory of classical physics.
Last time, we were really trying to wrap our heads around this idea that this theory, it uses classical physics to explain everything, like from the tiniest atom to the vast universe.
No quantum mechanics required.
Absolutely. It's a pretty radical concept.
It is.
But one of the most, I don't know, intriguing and maybe even controversial predictions of GUTCP is this idea of the hydrino.
The hydrino.
Okay, so remind me, what exactly is a hydrino? I mean, it sounds like something straight out of science fiction.
Yeah, it kind of does. But in simple terms, a hydrino, it's basically a hydrogen atom that's in a lower energy state than what standard physics considers the ground state, the lowest possible energy level.
Lower than the ground state. Isn't that impossible? It's like going below zero on the energy scale.
That's what conventional physics would tell us, right? But GUTCP, it proposes this whole different picture.
Okay.
Remember those orbitsphere electrons we talked about? Those tiny spherical bubbles of charge?
Yeah, I'm starting to get a picture of those in my mind. It's very different from those fuzzy electron clouds I learned about in school.
Very different. So in GUTCP, a hydrino, it's formed when a hydrogen atom's electron in its orbitsphere form shrinks to a smaller radius.
The electron shrinks. How's that even possible?
It's not about physically squeezing the electron. It's more about a transition to a lower energy level, a smaller orbit sphere, closer to the nucleus.
Right.
And the key to this transition, it's a catalytic process.
Catalytic, like in chemistry where a catalyst speeds up a reaction.
Exactly. So Phillips describes the scenario where a hydrogen atom, it interacts with another atom or ion, which acts as this catalyst, and that catalyst, it absorbs a very specific amount of energy from that hydrogen atom, allowing the electron to jump down to that lower energy level.
And that releases energy, like a tiny little atomic power plant.
In a sense, yes. And the energy released is significant. Like, we're talking about 200 times more energy than you get from burning hydrogen.
200 times. That's incredible. If these hydrinos are real, why haven't we seen them before? Why are they so elusive?
That's the million-dollar question that a lot of scientists have, right? And Phillips argues that they're difficult to detect because they interact with light differently than regular hydrogen atoms.
So they don't emit or absorb light in the same wavelengths.
Exactly. And that makes them invisible to our traditional spectroscopic methods.
So they're like stealth atoms, hiding in plain sight.
You could say that. They're not playing by the same rules as the regular atoms, and that has led to a lot of skepticism, of course, in the scientific community.
Of course. I mean, it is a big claim, and as they say, extraordinary claims require extraordinary evidence.
Right.
So what evidence does Phillips present to support the existence of these hydrinos?
He points to some specific observations that conventional physics just can't explain.
Like what?
Well, for instance, there are certain spectral lines observed in interstellar space and in plasmas that are generated in the lab.
Spectral lines, those fingerprints of light that tell us what elements are present.
Exactly. Phillips argues that these particular lines, they don't match any known element, but they fit perfectly with the predicted energy levels of hydrinos.
So if it's not hydrogen and it's not any other known element, what else could it be?
That's the argument, right. And it's not just spectral lines. Phillips also points to these excess heat measurements in certain plasma experiments.
Okay, so excess heat, meaning more energy coming out of the reaction than you put in.
Right, which seems to violate the laws of thermodynamics, right?
It does.
But Phillips says it's not a violation as long as you factor in hydrino formation.
So the excess heat is just the energy released when those hydrinos are created.
Exactly.
I see. But you mentioned skepticism earlier. What are the main criticisms of the hydrino hypothesis?
I mean, the biggest criticism is that it just goes against everything we know about the established laws of physics, right? The idea of an electron transitioning to a lower energy state than the ground state, it's just unheard of in standard quantum mechanics.
Right. It's like saying you can go lower than absolute zero.
Exactly. And critics also question the experimental evidence. They say that, well, maybe those spectral lines could be explained by other phenomena and that those excess heat measurements could be due to experimental errors.
This is a heated debate, so to speak.
It is.
You have this theory that really challenges the very foundation of physics, and it offers this potential solution to the world's energy crisis. But on the other hand, there's a lot of skepticism and a real need for more robust experimental validation.
Right. That's the scientific process at work. It's all about testing those ideas, gathering evidence, and ultimately refining our understanding of the universe.
It seems like we're at a crossroads with all of this.
Yeah.
What would it take for the Hydrino hypothesis to be widely accepted by the scientific community?
More research for sure.
More evidence.
Yeah, and definitely more independent verification. You know, if other labs can replicate the results that Phillips and his team are reporting, that would go a long way towards convincing the skeptics.
So it's a wait-and-see situation. But even if the Hydrino hypothesis doesn't pan out, it seems like Phillips' work with GUTCP, it's raising some really important questions about our understanding of the universe, isn't it?
Absolutely. I mean, it's challenging us to rethink some of our most fundamental assumptions about physics. And that's always a good thing, right?
It is. It's a reminder that science is this constantly evolving process, right?
Always.
We're always learning, always discovering, always pushing those boundaries of knowledge.
And who knows? Maybe one day we'll look back at GUTCP as the theory that revolutionized our understanding of the universe.
That's a thought-provoking note to end on. We've explored the atom, the electron, the nucleus, and this Hydrino.
What a journey.
Next time, I want to delve into some of the philosophical implications of all of this.
Oh, that'll be interesting.
What does GUTCP tell us about the nature of reality, about causality, the nature of the universe? Stay tuned for part 3 of our deep dive into the mind-bending world of Jonathan Phillips and the grand unified theory of classical physics. Welcome back to Teolumen Insights. It's Nathan Sinclaire here, and exploring the world of GUTCP with you has been quite the adventure.
I agree. I'm Emma Greenwood, and we've definitely covered a lot of ground, from those orbitsphere electrons
Oh, yeah.
to the Hydrino hypothesis.
Mind-boggling stuff.
Yeah, we've challenged some pretty fundamental assumptions about physics and even glimpsed a potential future with clean, nearly limitless energy.
Which is a very exciting thought.
It is. But today, I'm kind of curious about something a bit more, I don't know, philosophical. Like,
Yeah.
what does GUTCP tell us about the nature of reality itself?
That's a great question. And it's one that Phillips really grapples with in his work. You know, standard quantum mechanics, it's led a lot of physicists to embrace this view of reality that's inherently, well, probabilistic and uncertain.
Right, like that Heisenberg uncertainty principle.
Exactly.
Yeah.
That we can't know both the position and momentum of a particle with perfect accuracy.
So at that subatomic level, things get fuzzy and unpredictable. It's all about probabilities, not certainties.
Right.
And that's led some to suggest that maybe, just maybe, reality itself is fundamentally indeterminate.
Yeah.
That things happen randomly at that quantum level. But GUTCP, it offers a very different perspective.
A more deterministic view, a return to the clockwork universe of classical physics.
In a way, yes. Because GUTCP is based on purely classical principles, it suggests that reality is fundamentally deterministic.
Okay.
Everything that happens is a consequence of prior events and the laws of physics. No randomness, no uncertainty at that fundamental level.
So theoretically, if we knew the initial conditions of the universe and all the laws of physics, we could predict everything that would ever happen.
That's the implication, yeah. Of course, in practice, we can't know all the initial conditions perfectly.
Right.
But the principle of determinism, it's still there.
This whole idea of a deterministic universe has always kind of bothered me a little bit. I don't know. Does that mean we don't have free will?
You know, that's a deep philosophical question, one that, honestly, physicists and philosophers have been debating for centuries. And GUTCP doesn't necessarily answer that question of free will, but it does suggest that the universe operates according to a set of, well, fixed laws.
Like a cosmic clockwork mechanism just ticking away, everything unfolding according to plan.
It's a thought-provoking image, for sure, but even in a deterministic universe, there's still room for complexity and emergence.
Okay.
You know, the behavior of really complex systems can be incredibly difficult to predict, even if you know the underlying laws perfectly.
So even if the universe is fundamentally deterministic, it doesn't mean that it's predictable, at least not in a practical sense.
Exactly. Think about the weather.
Oh, yeah.
We know those laws of physics that govern the atmosphere, but we still can't predict the weather perfectly, right?
Right. There are just too many variables.
Too many interactions to keep track of.
Exactly.
And that goes for the universe as a whole. Even if GUTCP is right and the universe is deterministic, it doesn't mean we can predict the future with certainty.
So there's still room for, I don't know, surprise and wonder.
Absolutely. Plenty of room for that.
That's a comforting thought. I wouldn't want to live in a universe where everything was predictable and predetermined.
I hear you. And I think that's one of the things that makes GUTCP so fascinating. It challenges our assumptions about reality,
Yeah.
but it also leaves room for mystery and awe.
It does.
It reminds us that the universe is this vast and complex place, and we're honestly just starting to scratch the surface of its secrets.
Absolutely.
Yeah.
This has been an incredible journey exploring this radical new theory of physics,
It really has.
challenging the foundation of quantum mechanics.
Yeah, even thinking about the nature of reality itself.
And on that note, this is Nathan Sinclaire, signing off from Teolumen Insights. Until next time, keep those minds curious and those imaginations firing.